Hello everyone and welcome to the Solid State Watch. I'm Shannon Davis, the web editor for Solid State Technology, and now let's take a look at the top stories we've been tracking from December 4th through December 10th, 2015. Worldwide semiconductor fab equipment capital expenditure growth for 2015 is expected to be 0.5%, increasing another 2.6% in 2016, according to the latest update of the quarterly Semi-World Fab Forecast report. SEMI reports that in 2015, Korea outspent all other countries on front-end semiconductor fab equipment and is expected to drop to second place in 2016 as Taiwan overtakes the largest capex spending at $8.3 billion. In 2015, America is ranked third in overall regional capex spending with about $5.6 billion and is forecast to increase only slightly to 5.1% in 2016. NXP Semiconductors and Freescale Semiconductor announced the completion of the merger, which has created a high-performance mixed signal semiconductor industry leader with a combined revenue of over $10 billion US. The combined enterprise values at just over $4 billion. The merged entity will continue operations as NXP Semiconductors and has become the market leader in automotive semiconductor solutions and in general purpose microcontroller units or products. One of the greatest challenges in the evolution of electronics has been to reduce power consumption during transistor switching operation. In a recent study, engineers at the University of California, Santa Barbara, in collaboration with Rice University, have demonstrated a new transistor that switches at only 0.1 volts and reduces power dissipation by over 90% compared to MOSFETs. A minimum gate voltage change of 60 millivolts at room temperature is required to change the current by a factor of 10 in MOSFETs. In essence, the existing state of transistor technology limits the energy efficiency potential of digital circuits in general. The research group at the University of California, Santa Barbara, took a new approach to subverting this fundamental limitation. They employed the quantum mechanical phenomenon of band-to-band tunneling to design a tunnel field effect transistor, or TFET, with sub-60 millivolt per decade of sub-threshold swing. At this week's IEEE IEDM conference, Nanoelectronics Research Center IMEC showed for the first time the integration of high-mobility indium gallium arsenide as a channel material for 3D vertical NAND memory devices formed in the plug with the diameter down to 45 nanometers. The new channel material improves transconductance and read current, which is crucial to enable further VNAND cost reduction by adding additional layers in 3D vertical architecture. To boost the drive current in the channel, IMEC replaced the polysilicon channel material with indium gallium arsenide through a gate first channel last approach. The channel was formed by metal organic vapor phase epitaxy showing good 3,5 growth selectivity to silicon and holes filling properties down to 45 nanometers. The resulting 3,5 devices proved to outperform the polysilicon devices in terms of on-state current and transconductance without degrading further memory characteristics such as programming, erase, and endurance. For more industry headlines during the week, be sure to follow us on Twitter or like us on Facebook. For Solid State Technology Magazine, I'm Shannon Davis. Thanks for watching and see you next week.